All right. So let me know if you can see the screen. 1 second. All right, full screen. Okay. So the screen is visible for everyone.
Yes.
All right, perfect. Good. So we have 2 students at this point in the meeting. I always try my best to wait for students, but it's always recommended that you join on time because then it delays the lecture a bit as well. But at the same time, I don't want anyone missing out on the class. We have 3 students as well. Okay, I think now let's start now. So for those who have just joined, we'll be doing past paper questions from the first topic. Today we'll be mainly focused on this exercise. Is there any question from previous lectures or all of the lectures that we have covered so far? Is there any question from those lectures at this point? I was also expecting you students to send me some questions on WhatsApp so I could figure them out and then we could discuss them in the class. But apparently there was no question. I'm also guessing that this topic is not really a very tough topic. So that's why there might not be so many questions as well. Let's see after we solve today's past paper questions, we might have some questions in the next class. All right, so everyone can hear me clear?
Yes.
All right. So let's start. We'll be doing this first question. The question reads that we have a mass and it hangs on a string which is fixed at point P. We can see that it starts from position 1. So that's position 1. That's where the system is starting. And it swings to the furthest position on the opposite side, and that is obviously position 2. It then oscillates several times with decreasing amplitude before ending at position 3. So what he's saying is that you have this oscillation, it was over here, you really brought this pendulum to this point and then you released it, and that's where it started its journey and you started timing it. So at this point time was 0, and then the time started from this point. Then it started oscillating, went from 1 to 3 to 2, and then kept oscillating. And because of the air resistance, frictional forces, and whatnot, it eventually came to rest at position 3. So if it came to rest at position 3, this means that this is the mean position. Does everyone agree with that?
I can.
Right. Sorry, I'm having some trouble hearing you. Can you repeat? Did you ask something, or this is clear,
I
right?
agree. That's the. Yeah,
Okay, perfect. Right. Okay, so and the point that you released it from, that is the extreme position. Extreme position. Now, you're asked, where does the ball have the most kinetic energy? So you have some options: position 1, 2, the first time at position 3, the last time at position 3. So what do you think? When the first time really means when it comes to position 3 and then it again starts oscillating. The last time at position 3, what that means is when it has, last time is the point when it has come to rest, right? Because according to the question, he said that before, so it will keep oscillating 1 3 2 2 3 1 1 3 2 2 3 1. This will keep happening until it comes to a stop at position 3, And the last time, what it mean, this option means is that the last time is when the pendulum has stopped, it's at rest. So when do you think will this ball have the highest amount of kinetic energy? Anyone from the students?
I don't know. That would be A.
Sorry, can you repeat? I cannot hear your voice clearly. Can you come closer to the mic? Sorry.
That would be A. That would be A.
Okay, so you think the kinetic energy would be maximum at position 1. Is there anyone
Yes.
else who thinks otherwise?
It's either A or C. I'm not sure.
Okay, so you think it's either A or C. A is at position 1, C is the first time at position 3, right? So both are literally the opposites of each other, really. Okay, so you said the first person, Taha and Muiz, you said that it's position 1. Why would you say that it's position 1? What makes you think that the kinetic energy would be maximum at this point?
Because it's when the person releases the ball, hanging ball.
Okay, so you think
So
he's going to release the ball and it's going to gain some
have more
velocity,
energy.
right?
Have more
Okay, okay,
energy.
okay. What about you, Urva? Why do you think it's either A or C?
I'm not sure. It can probably be C as well, because when the ball is released at one position, I don't know how to explain it. It probably gathers up more kinetic energy at what is that called? Position 3.
3,
So
right? Okay.
yeah.
Okay, so yeah, so that makes sense. Okay, so now Taha, okay, we have two names in this thing, Taha and Muiz, I think. Which one are you, Taha?
I am Taha and I have my brother Moish.
Oh, okay, okay, right. So Taha, you said at position 1, but remember, okay, what happens? What happens when I have a ball and I raise this ball to some height? Suppose you're raising this ball to some height h. The ball gains some potential energy, right? So when you're raising anything
Yes.
to some height, okay, right, yeah. So you're raising something to some height, it gains potential energy. So because of the conservation of energy, there are two forms of energy at this point. And if this is maximum, then kinetic energy has to be minimum, because the energy must be conserved, right? So at position 1, the potential energy really is maximum, right? Because that's the maximum height that I have raised the ball, and then I'll release it. Now when I release it, for example, this is a bar which represents potential energy, and this is a bar which represents kinetic energy. At this point, the bar is just 0. What happens when this pendulum starts moving towards position 3 is that the potential energy keeps decreasing and the kinetic energy keeps increasing. So what will happen at one point, potential energy becomes 0 and the kinetic energy becomes maximum. Now that is this position 3. Because now when it comes to position 3, it is almost, you can say it is, well, you cannot just say, it really is at the position of rest, really, which is the mean position. And at this point, it will start to gain velocity again to start moving towards position 2. And then the kinetic energy starts decreasing, and potential energy starts increasing. Right? So
Yes,
the
understood,
maximum.
understood.
Okay, right. So is that clear for everyone? So the correct option would be option C, because it will
Yes.
not be option D. Why would it not be option D, by the way?
Because it's the last time it would be in rest. So it would either have
Right.
potential or kinetic energy.
Exactly. So it would be at rest, and so at that point, there will be no velocity, no height, nothing. So it will just come to a stop because of the frictional forces, and so both the potential and kinetic energy would be C. So is that clear for both of you, Taha and Urva?
Yes.
Okay, perfect. So then we can move on to question 2. Okay, here we have it. So it says, it's a Vernier caliper question. It's a very simple one also. We have a diagram, and this diagram shows 2 different scales. We have V and S. Now V is really a Vernier scale, and S is your main scale, for example. Now,
Or fixed then.
yeah, exactly, or a fixed scale. So we're asked the Vernier reading. What would be the reading that I would get from this this arrangement? So if you look at both Vernier and fixed scale, what do you think would be how would you go about this problem? For what value should I look to determine the value, the Vernier reading really? We start by looking at the Vernier's 0, right? Wherever the Vernier's 0 meet the fixed scale, that is the reading that this is showing you. The Vernier reading that this is showing you. Now, look at the fixed scale. We have 2 over here. We have this. We have these divisions, and 3 is over here, which means that the divisions are. So if I say that this is 2.1, 2.2, 2.3, 2.4, this is 2.5, and you can go on to 2.9 and then 3, right? So that's 2.6, 7, 8, 9, and then you come to 3. So now if you look at this division, this 0 is really coinciding with this scale at this point. Now this line lies in between 2.3 and 2.4, but it's behind the halfway of 2.3 and 2.4, because the halfway of 2.3 and 2.4 is this line. I think I should use some other color. So this blue line really is the halfway between 2.3 and 2.4, and the 0 on the Vernier meets the scale S at this point line where I drew this black line really. So then what could be the Vernier reading? Anyone? I have more or less I have explained the
Yes,
method.
I have an answer. Is it C? Because it's near 2.3 and before 2.5.
Exactly.
So
Yeah.
it's before 2.5.
Yeah, it has to be before 2.5 and it has to be greater than 2.3. And the only option for that is this option C, right? So is that clear for you as well, Urva?
Yes.
Okay, perfect. So that was this. Then let's. Okay, so here we have a question, and it says that a journey is happening, and it consists of 2 displacements. Now remember, displacement is vector, or you can use a vector to represent displacement. Now the first is 500 meters in north direction, and the second is 200 meters in east direction. So we have 2 displacements, So person really starts its journey. Person moves to the north, and then he moves to the east, right? So you all understand the directions, right? This is the upwards is north, east is to the right, and then the rest are easy to figure out. So the opposite of north is south, and this is west, right? So we are required to draw, to scale a vector diagram of these displacements. State the scale of your diagram. On your diagram, show the two displacements and the resultant displacement as well. So what would be the resultant displacement from occurring from these two different displacements? That's what we have to show. Determine the size, which is the magnitude and the direction of the resultant displacement. So what should I do? What's the first thing that I should be doing at this point? I'm required to draw a vector diagram, right? A vector diagram, a graphical representation of vectors. And so I have to draw two vectors really. So what's the first thing that whenever you are going to draw a vector diagram, you should specify or do that first thing? What is that? Anyone? Okay, so remember, in fact, they even specified it in the question. Always, whenever you are drawing a vector diagram, the first thing is always to specify the scale that you would be using, which really means that how many, or let's say 1 centimeter line that you're drawing on this paper is equal, or it's equivalent to how much displacement that I'm going to, how much of the vector that I'm going to draw is. So it could have been a force. Remember, we did an example in the class where we did the same thing for force. Now here we have to specify a scale, and we have to specify in such a way that 1 centimeter on my paper is equivalent to how many meters of displacement. So what would seem a, what scale do you think? How many of meters should I say that 1 centimeter is equal to, so that I can draw it on a paper with ease?
Probably 100. Or
Yeah, 100 is a good option. 100 is a good choice. I mean, 100 meters, because if you were to say 10, then you would have to draw for this thing. How many centimeters would I have to draw? 50, right? Which would not really make sense, because so you get it, right? But now in this case, I just have to draw 5 centimeters for north and 2 centimeters for this east direction. Drawing 50 centimeters on a page is not sensible, right? So this is a good choice of scale. Great job. So we have specified the scale now. What is the next step that I should be doing? We have really indicated the north and east directions. So that's also, you should always remember to indicate those as well. We have done that. And now the next step is just to draw these vectors. So we'll say, for example, just draw a point over here and say, this is where I'm starting my journey from. And let's call it point O. Now, the first thing is that you have to move to the north. North is, they have even specified it for you. It's in this direction. So you will draw how much centimeter of a line in this direction?
500 or 5 meters.
5 centimeters, right? Yeah, so you'd be drawing a 5 centimeters line, which would correspond to 500 meters of displacement. Now, first he moved to the north 500 meters. Then secondly, he moved 200 meters to the east. So I'll draw a 2 centimeter line in this direction, right? Now, I don't have a scale with me at this point, but when you would be doing this on the paper, you would make sure that you use a proper scale and draw it accurately, right? So this would be a 2 centimeter line, which corresponds to 200 meters, right? So is this clear, the drawing of these two vectors?
Yes.
Okay, so first I drew from point O, which was any starting point really. And because he said that first he moves 500 meters to the north. So that's why I drew a line which is 500 meters in displacement in the upwards direction to the north. And then he moves, secondly, 200 meters to the east. So when he moved to the north and he stopped, then he'll move to the east. So after that, I'll draw this second line, which is 2 centimeters to the east. So is that clear for everyone? Taha and Urva?
Yes.
Yes,
All right,
understood.
perfect. So we have stated the scale of the diagram. That's done. On your diagram, show two displacements. We have shown two displacements. Now we have to show the resultant displacement. Where would the resultant displacement be on this diagram? The resultant displacement is from
I
the
don't.
okay, so it's the resultant displacement is always from the tail of the first vector to the head of the second vector, right? And now imagine this in your head. Imagine that you're walking on a straight road, right? And you walk in this direction, and then you walk to the right in this direction. Wouldn't it be the same thing if I walk from this point where I started my journey and I walk directly to this point? It would be the same thing, right? So the resultant of these
I don't
two,
think so.
you don't think
It
so?
is the
Okay,
same thing.
can you give me, yeah. So can you give me a reason for that?
Well, near my house, there's a track. So I always just takes the resultant way.
Yes, so it's really the same thing. If you had taken this approach, this one, and then you move to this side, the only thing is that the length of the path would have increased, but you started from your house and you would end at this point. At the same time, if you're starting from your house and moving diagonally like this, you're still ending at the same point. So the result is still the same. However, this vector is shorter compared to these two vectors. The sum of these two vectors. Is that clear?
Okay. That's clear. That's clear.
Right? Okay, so it's clear for you as well, Urva?
Yes.
Okay, so that's why I drew a resultant like this. But now there is just a rule that you can also follow. So this was just physically what is really happening. So I told you to imagine the situation as well. But you can just follow this rule that whenever you want to find the resultant of two vectors, you start from the tail of the first vector and reach to the head of the final vector or the second vector. And then you just draw that line, and that's your resultant vector. So we'll call this some vector R. So this is the resultant vector. All right, so we have done this part as well. Now, he says at the end, determine the size and the direction of the resultant displacement. So that's pretty simple, right? All you have to do really is just use a scale and measure the distance from, I'll use some other color, this point to this point. Just put a scale on this vector r, measure the distance, and then use this scale, and you can find your answer in meters. So is that clear?
Yes.
Right? Okay, good. So it's clear for everyone? How will we find the resultant
Yes.
magnitude of the resultant vector? Okay, it's clear for you as well, Urva, or is there any confusion? If you have any question, feel free to let me know. If you did not
again.
Okay, so this R part, how did we find the resultant? That's the part that you're asking. Okay. Okay, so really what happens is that you understood this part from, I started my journey from point O, and according to the question, I moved 500 meters to the north, and then I moved from there 200 meters to the east. So that point is clear, right?
Yeah, that's clear.
Okay, good. So by the way, you can see this pointer. You can see my pointer.
Yeah.
Okay, 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 good. All right. So now the resultant of these two, resultant just means ke, both of you understand Urdu, right?
Yes.
Yes, of course. Yeah.
Okay, okay, amazing. So it's just an O-level class. Sometimes we have students understand Urdu, so that's why I just asked. So resultant really means ke is cheez ka, final result kya hai, ke like, what is the final thing that happens if I take these two vectors and I, for example, in this case, we are walking. So you're walking, you start your journey from this point, you walk to this point, and then you say, I want to make a turn. You make a turn, you come to this point, and you stop at this point. Now, what else you could have done? For example, there was no barrier in between your path. You could have just taken this point and taken this journey, right? So you could have just taken this journey and you could have still reached to that point. The difference, so that's the result. That's the resultant of these two vectors. So that's what happens. Now, if you imagine this situation in your head, you could imagine in your room, maybe or maybe just outside somewhere in the ground or something. You walk this distance and then you walk this distance, or you have maybe have your brother or sister or your friend tell them to take this path. So both of you, one takes this path and one takes this and this path. Both of you will reach this point, obviously, because that's where you're going. The only difference is that this person 2, will reach his destination first, while you might lag behind a bit in an ideal case. For example, if there is no barriers between the paths, right? Because the resultant of these two is really shorter than the sum of these two vectors. And we can find that as well by using mathematics. You can compute, remember, r squared was square root of these two vectors, any two vectors. So in this case, this vector is 500 meters. So 500 squared plus this one is 200 meters, 200 squared. So if I compute that, I get something. Okay, so I'll have to do it because I'm not that smart. 500 plus 200 squared. It's 430 something, right? Square root of this answer. Okay, apparently I cannot take a square root of this calculator. All right, so it's actually 538.51 meters. Right? So that's the value of R. If I just added these two vectors together, so suppose instead if I added 500 meters, first I walk this length and then you walk plus 200 meters. Then the resultant is, then the sum of these two is 700 meters.
700.
Right? Good. So you can clearly see that this is way smaller compared to this thing. But the end result is still the same. You both are reaching this point, whatever this point is, let's call it point Q. You both are reaching that point, but this person 2 will reach, probably he'll reach first, and person 1 will take some time to reach, provided they're both walking at the same speed, right? Obviously, if person 2 decides to slack off, get lazy, sit down, start eating and all, he'll reach later. You could argue with that, but provided they both are moving at the same speed, so a person 2 would reach point Q first. So is that clear? Is the idea of the resultant clear? Now you could just follow a rule. Okay, great. So you could just also follow a rule, and that is that if I have any two vectors, right? So if I have this vector and I place those vectors in this fashion where I put one vector, draw one vector, and the second vector, I put its tail to the head of the vector that I drew first. And then you get something like this. Then just simply draw from the tail of the first vector to the head of the second vector. Draw a vector like this. This vector that I drew will always be the resultant. This thing is also known as head to tail rule of adding vectors. Why? Because I drew this first vector and I placed the second vector tail first on the head of it. So I had my second vector and then I added or then I just drew from the tail of the first vector to the head of the second vector. I drew a vector which gave me this resultant vector. So that's one of the rules that you can always follow to add two or more vectors. Is that clear now?
Yes.
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 Okay, great. So we have shown the resultant displacement, and so the next thing was to determine the size. We'll just put a, because now the same way we drew these vectors, right? We defined a scale and then used that scale to draw these vectors.
Sir, you already done the size as 538.5 meters. 51 meters.
Yeah. Yes. So that what this thing is done. That was just me proving this point that this path R, the path which is labeled R, that is smaller compared to the path if I go from this to this point. Right? So that was just doing that. This is mathematically, but in the question they have asked you to do it graphically, right? Because they have said that draw a vector diagram of these displacements, and then using this diagram we have to show. So that can be simply done by using a scale now and measuring from this blue circle to this blue circle. So just put a scale on this and then measure it, whatever, you'll get something in centimeters. Then use this scale to convert, go from those centimeters to any value in meters. You would be getting this something closer to this value.
Yes.
So is that clear for everyone, Urva and Taha, both of you?
Yes.
All right. So is that okay for you as well, Urva?
I'm sorry, I didn't know my mic was not muted. Yes.
Okay, no problem. All right, okay, great. So that was very simple. Now you have to find the resultant displacement's direction as well. So how can I do that? I'll just use my protractor, right? You can put a protractor on this and then just measure the angle. Now it doesn't matter where I put my protractor. Obviously, you have to put it on the resultant vector. You could have also put it over here as well. Let me just use this other color for protractor. So this thing, blue thing, both places it would work, but you would have to then specify from which vector direction are you measuring. So if I'm measuring from this one, then you would say this much, whatever the